Hi, I'm Jason Rohde, coming to you from NOMAD Creative Studio in Montreal, live 24/7. In the context of the COVID-19 pandemic, water infrastructure resiliency is more important than ever. On June 2nd, Cornell University's School of Civil and Environmental Engineering issued its final report, Performance Evaluation of Aquapipe under Earthquake-Induced Ground Deformation, which details technical findings confirming that SANEXEN's next generation of water technology is proven to withstand severe earthquake conditions and natural disasters. Experts Martin ORourke, VP Innovation at SANEXEN, and Professor Thomas ORourke from Cornell University will share how the resiliency achieved by the Aquapipe technology has exceeded all known standards and outperformed every other solution on the planet, and what it means for cities and municipalities across North America. The webinar will outline how the next generation of water technology delivers the highest degree of resiliency, reliability, as well as being sustainable for the environment and the economy. Gentlemen.
Good morning.
Hello. So where are we calling in from? Martin, where are you?
I'm in downtown, close to downtown Montreal.
And Mr. O'Rourke?
I am at my home in Ithaca, New York.
I see. Well, thank you both for being with us. Martin, can you tell us a little bit about yourself, how long you've been working with SANEXEN, and what's your general experiences?
Yes, I've joined SANEXEN a little more than 7 years ago. At the time, I joined to organize their research and development efforts.
So this is how long ago, you said?
7.5 years almost.
7.5 years ago. And where were you before?
I was with the National Research Council of Canada. This is the premier R&D organization of the federal government in Canada. I was working in a specialized institute in manufacturing and materials, especially in the group of composite manufacturing. The link between myself and SANEXEN is the following. When the city of Montreal started working on improving their water preservation statistics, they discovered that they needed to fix their water main leaks because they were flooding the overall system, the sewer system in particular, and that led to a lot of public money wasted, because the more water you have in the sewer network, the more water you have in the sewer network, the more you need to treat, and the more expensive it is, and all the water main network was leaking into that sewer system.
Wow.
So you pay twice. You pay for the treated water that you lose, and then you pay for the sewer water, the wastewater that you have too much of. And they came to SANEXEN to ask for a solution. Do you have a solution? And we probably came to a number of companies. So they came to us and to see how we could figure a lining material that would be both safe, reliable, and durable. And that was actually my first PhD. I just had finished my PhD thesis, and that was my first real applied industry work at the time. That's in early 1998.
Okay.
And we worked together for 7 years, I believe, on various projects. First on the architecture of what is now Aquapipe, first generation, and then on improving their resin quality and eventually formulating their own resins, which would be proprietary and NSF approved, of course, NSF being one of the standards that we need to meet for potable water contact. And we did a bunch of research, and eventually they decided to do their own research. I decided to join the company.
And what have you been doing at SANEXEN since you've been there?
We created a group of, we call it the Research and Development and Engineering Group. The leaders at the time and our leaders today had the vision of investing in technology to make a difference and better answer our clients' needs.
And what involvement did you personally have in the development of the Aquapipe, you call it?
Aquapipe Generation 2. Well, first of all, the first generation was really created in my lab. So the SANEXEN team did a fantastic and very outstanding job in getting that product to be, to install it properly, all the operations aspect of it. The robotics were a huge effort on their side. But the material per se, the one we'll discuss during the talk, is something that was born in my lab. So we designed it. We designed all the process of impregnation with the resin. We made sure that the properties were there, and so on. And obviously, Generation 2. Well, when I was working at NRC, I knew that we could do more. But then, I mean, timing needs to be there. The investments need to come at the right time, and we never did it. But when I joined, I made sure that we'd have the right IP in place, so all the patents.
As I understand, you two have a relationship. How do you two know each other?
About 5 years ago, we were working on a demonstration of the resiliency of our product. And I started talking about people who were interested in that topic, water utilities being the main source of information. And they all pointed back to Tom's work and Tom's lab. So we had started some work down here in Canada with the National Research Council, but it really became clear that we needed to reach out to Cornell's expertise at that time. And then a colleague of mine, Gilles Gagnon, and myself drove down in the beautiful region of the Finger Lakes in Western New York State, and came to visit Tom at the time.
What does your work consist of, Professor?
We generally look at the performance of pipelines or conduits or cables, underground infrastructure at large scale, at the scale that actually exists in the entities that one puts underground.
We actually performed a fault rupture test on a 6-inch diameter iron pipeline, and it's lined with SANEXEN Aquapipe Generation 2. So we have something like 138 or some odd instruments attached to the pipe. We then filled it with soil, and we ran a fault rupture test.
So, for example, if we test a pipeline system, we typically will test a very convenient and universal sized pipe, something on the order of 150 millimeters, something of that sort. And we'll run a series of tests on it. We also, and I think this is unique to our lab, is we're able to characterize the performance of a whole variety of different underground facilities. And we're also able to analyze those. We have various modelers who can model the performance of these systems so that when we do large-scale tests, we actually can convert what we know from large-scale into numerics, so we don't have to repeat the test. We can actually take the data that we've generated and actually come up with models that people can do engineering and analysis for. In addition, we also model large systems. For example, we were among the first, in fact, I think we were the first to develop what we call a hydraulic network model for water supply. That was in San Francisco. We actually worked with a couple of firms and the fire department in San Francisco, and were able to model what they call the auxiliary water supply system. And they made some policy decisions and some planning decisions based on what we did. And based on what we did, we were able to, with the fire department, at least the fire department was able, with our assistance, to put the fire out in the marina in the 1989 Loma Prieta earthquake. Since that time, we've actually modeled the entire 10,000 kilometers of different pipelines and couplings and connections and different types of tanks and reservoirs for the Los Angeles Department of Water and Power. And they've made some policy decisions based on the large models that we've created for them too. So we were able to cover all aspects of the spectra associated with underground infrastructure, particularly with respect to water supplies, with respect to energy delivery systems.
So it sounds like you've been working in this field for, well over 30 years.
We've been actually working on it for slightly over 40 years. Among the first research projects I ever received was support from a company that was then called Brooklyn Union Gas. And Brooklyn Union Gas was leading a group of gas utility companies to look at their inventory of cast iron, which in those days was tens of thousands of kilometers of cast iron mains, and to make some decisions about the performance of that cast iron with respect to adjacent construction, and to make some decisions with respect to their risks and what they needed to adopt in terms of replacement and risk mitigation strategies. So we started working with Brooklyn Union Gas. That immediately led to connections with the Consolidated Edison Company of New York, with New Jersey Public Electric and Gas, and so forth. And we were able to develop a series of procedures that they eventually adopted and used in the field. And that work actually grew because at the same time, we were putting in proposals to the National Science Foundation in the United States for the behavior of pipeline and pipeline systems during earthquakes. And we managed to have many years of support and funding from the National Science Foundation. In fact, we were a principal investigator with what was then called the National Center for Earthquake Engineering Research. It was instituted in about 1986, 87. It went for about 10 years and then transformed itself into the Multidisciplinary Center for Earthquake Engineering Research. And that went for another 10 years or so. So we had about 21 years of support from the National Science Foundation in terms of the earthquake performance of these kinds of systems. And then in 2003, we put in a successful proposal to what was then called the National Network for Earthquake Engineering Simulation, NEES. And the NEES was successful, our proposal was successful, and with that, we built an indoors laboratory facility, which we are using for the pipeline products for SANEXEN. And we were able to establish and build this thing with a very generous grant from the National Science Foundation, and they supported research at Cornell for about 10 years. And that brings us to about 2013, and at that point, we had developed a lot of contacts with industry, both in particular water, but also with the gas industry, and then started getting telephone calls and ended up performing more research industrially, that is for our sponsors from various industry sources. It eventually replaced the National Science Foundation support. And to this day, we're doing large-scale pipeline response. We're doing work with the utility companies. We're doing work with various producers of gas facilities. And we're able to do this at a scale and put it into context, put it into practice, put it into to the right kind of organization for our clients. And we've been particularly excited about the work that we've done with SANEXEN, with the liner products and so forth. They've been extremely good clients and very, very helpful and useful to work with. We've learned a lot, and hopefully SANEXEN has at the same time.
No, we surely did. Tom, before we get to our main topic, I understand that Brooklyn Union Gas work eventually led to probably pioneering work on cured in place lining methods for gas, which was probably the first work done on somewhat resilient assessment work in the world, I believe.
Yeah, the gas industry became quite interested around 1998, 2000 in rehabilitating pipelines in situ. And we ended up testing some linings, a Starline 2000 lining. It's a cured-in-place pipe liner, not a cured-in-place pipe like SANEXEN's product is. And we were able to characterize and do testing on that specific lining so that they could line cast iron mains parallel to excavations for sewers and water lines and so forth. And even though those would generate differential settlement, they wouldn't generate a lot of lateral movement, but they would generate differential settlement or differential movement, rotation between the joints. Not a lot of axial extension or contraction, but some differential rotation and settlements. Those materials we were able to validate and manage to get them into practice for people.
And that's to close the loop. That's really what attracted our interest, because this was a lab knowing about water mains and other type of pipelines, but also rehabilitation techniques, which you generally don't find. I mean, it's either renewal, replacement stuff, or rehab. And Tom, I think it for sure in North America is the only one that does it too.
We were very fortunate in the sense that we had strong industry support from the gas industry for this kind of research. And we had strong support from the National Science Foundation. We actually had a 3 to 4 year project with the National Science Foundation to look at the behavior of linings during earthquakes. And that allowed us to affiliate with the University of Buffalo, who had dual shake tables, so they could look at the large-scale performance dynamically, and we could look at the large-scale performance from a ground rupture point of view. We have special facilities that really no one in the world has quite the same facilities as we do for looking at the performance of pipelines and pipeline systems crossing faults. And of course, faults are meant to be a demonstration of differential movement. So you may have an actual ground rupture that's a fault during an earthquake, and you need to survive that. We can test that explicitly. But we also realize that permanent ground deformation is what happens at the margins of landslides. The most significant deformations imposed on pipelines in landslides is where they cross from the landslide area to the stable ground adjacent to the moving area. And where they cross, it's almost like a fault. It's very similar. Yeah. So we actually characterize and look at those kinds of behaviors. The same thing applies for liquefaction.
There's a reason I wanted to bring you two together, because quite recently, a few days ago on May 15th, in a remote area of Nevada, I'm sure you've heard of this, there was a 6.5 magnitude earthquake which ravaged the area. You could see some rather apocalyptic cracks, crossroads, and so on. And this made me think of our work with SANEXEN, of course, and what you've done with Aquapipe, and what the technology that you've tested at Cornell, Professor, how this technology could help in such a case. Could you perhaps, do you know about this event in particular, and do you have these kinds of reactions when you hear about this?
Well, one of the major vehicles for learning about earthquakes is to go to areas that have been influenced by an earthquake. So the community that deals with earthquake engineering, the engineers, the geoscientists, the social scientists, and and whoever, actually goes out to these sites. So I knew about it virtually when it occurred. Some of my friends have gone out to Nevada and have investigated. I just came back from New Zealand, where I was on a sabbatical leave from Cornell. And in New Zealand, of course, that's a dynamic area. They have big problems with respect to earthquakes, and therefore have to have utility systems that are able to survive the kinds of ground movements that are caused during earthquakes. And in New Zealand, they've had some major earthquakes in Christchurch. I happened to be in Christchurch at the University of Canterbury, Christchurch. And they had a sequence of earthquakes primarily from 2010 to 2011 called the Canterbury earthquake sequence, 4 major earthquakes and many years to recover from those earthquakes, recover with respect to buildings and water supplies and so on and so forth. And I played a big role in the restoration of Christchurch. Since then, they've had the Kaikoura earthquake, about a 7.8 magnitude earthquake up at Kaikoura north of Christchurch, maybe about halfway between Christchurch and Wellington, which is the capital. And most recently, there was a 5.5 or a 5.8 magnitude earthquake near Wellington a couple days ago that was just offshore. So we live in a pretty dynamic planet, and we're constantly reminded of these earthquakes in Nevada, in New Zealand, about the significant effects. And certainly everyone who owns a water supply on the West Coast and a variety of states in the Western states, as well as the entire United States, about 43 of the states carry a significant earthquake risk, has to deal with the effects of earthquakes as part of the design and fundaments of those systems. And we try to help out as best we can by pointing out what they need to do, but most importantly, by working with companies like SANEXEN that allows us to actually take real products, work with people that are pragmatic, that have to make something work both technically and make it work financially. And that's where we cut our teeth. We're able to work with real products at the full scale that they're being utilized in, and help to characterize those products and put them in the right direction, and to provide as much support as we can.
So let me understand what that work consists of, what you two have done together, and how it applies here.
There was a series of testing that was done by SANEXEN that demonstrated quite clearly that our product was able to withstand large-scale deformation at ring breaks, for example, at ring fracture in a given pipeline. So picture a pipeline, you have a crack or a joint, and for some reason it bends or it moves a little bit.
Does this only happen in the case of an earthquake, or can it happen?
No, a freeze-thaw cycle that we get in our cities, Montreal, Winnipeg, Toronto, has those all the time, actually more than other places prone to seismic events, although those movements are less important, but still quite significant. And our product has that ability to withstand very significantly that deformation, that strain that's imposed by the surrounding of the pipe. Most, if not all, of the other products that are used for lining water mains do not have that large-scale deformation capacity. So we had that data, but it was kind of highly empirical, non-controlled, yet third-party and independent. We needed to go, the extra mile and get something that's recognized. And as time went on, we were talking in particular with Los Angeles Water and Power Department. And they told us, well, you claim that, you need to assess it with Professor O'Rourke. And their seismic or earthquake resilient expert over there, Craig Davis, and Tom were instrumental in getting us that old program that we launched at Cornell.
So we're talking about basically testing the adaptive capacity of a pipe.
Exactly. So we had that old set of data that's about 5 to 7 years old at least. So we decided to take our technology and improve it even more, and get to our next generation of Aquapipe, where we have a product that's able to adapt to the internal diameter of a pipe, conforming perfectly to it, and while maintaining the resiliency and even improving it. And we went to Tom to make that demonstration. And perhaps, Tom, you could complete on how this was tested at your facility.
Yeah, I'd like to maybe expand on one point you made, Martin, and that was that large movements occur not only during earthquakes. You may get them from freeze-thaw cycles, Of course, Canada is subject to freeze-thaw, all utilities in Canada. And similarly, in New York State, there's a lot of freeze-thaw activity that goes on. But we actually call our expertise an expertise in hazard resilience. So not only are we going to advise and do testing to reinforce products to be earthquake resistant, but we're gonna do it to make them hazard resistant. So some natural hazards cause differential movements are hurricanes. Large flooding events cause regional subsidence and actually have washouts, undermined pipelines, cause movements that something like a lining system can resist, and therefore they can perform after the hurricane and not have to be replaced as quickly or replaced at all. So that's one part of hazard resilience. Other parts of hazard resilience might involve mining subsidence, might involve construction from tunneling or adjacent excavations, which often cause ground deformations, and might actually involve growth faults, regional subsidence from withdrawal of water. For example, in Arizona, they actually have normal faults that develop at various locations in the groundwater basin there and cause concentrated deformation, because as they withdraw the water from the Arizona location, they're causing regional subsidence, and that regional subsidence manifests itself in terms of local differential ground movement that affects whatever is buried in those particular locations. So there's really quite a lot of sources of permanent ground deformation. Normally, when we do testing, we not only look at the performance of the pipeline with respect, or the facility underground that we're looking at, with respect to permanent ground deformation in terms of fault offset. That's the worst form. That's the most abrupt, most concentrated deformation. We generally found that if we can model that, which is a proxy for the margins of landslides and liquefaction. So not only are we looking at fault movement, but we're looking at landslides, we're looking at liquefaction, we're looking at differential settlement, if you want, and differential horizontal movement. So we cover all of that. And not only do we look at the performance with respect to permanent ground deformation, but we have a protocol where we thoroughly examine the performance of the system that's supposed to be subjected to differential movement. So, for example, we do tests on tensile coupon tests, on really carefully done testing that supports or amplifies what the product people have done. SANEXEN, by the way, has done some excellent tensile coupon tests where they understand the stress strain behavior in different directions of their lining material, both in the longitudinal direction along the length of the lining and also in the circumferential or transverse cross sections. But we try to duplicate those tests and perform our own to either back up the data or provide additional perspectives. We look at the direct tension and direct compression of the pipelines. We look at bending deformation of the pipelines. And particularly, we've developed a special expertise here. We look at 4-point bending tests. That way we have a constant moment that's applied to a particular joint. In this case, the joint would be lined with the SANEXEN lining material. And we can characterize the moment rotation relationship of these particular joints, which is tremendously important. And we actually sometimes will look at the axial soil resistance that just gets developed as the pipeline moves in the ground longitudinally. And we combine all of this work with respect to ancillary deformations, and we numerically use that information in a model of a big fault rupture that we do before we do the actual fault rupture test. The fault rupture test is quite complex, and therefore we have to give it a full numerical analysis ahead of time using the results that we've gathered from the other tests. And we did that. And we get an idea for how much deformation can be sustained. And then we run our test and we see how much deformation is actually sustained. So there are things we can do in terms of prediction, but there's things that we can't do in terms of prediction. Only a large-scale test can do those. Once we have the information, the data from the large-scale tests, we can refine the numerical models in the way that they need to be refined and therefore can substitute numerics for actual testing in the future.
So, by the way, before we ran the large fault rupture test, I remember you had some internal predictions on how far we would go, which you never really shared. You gave us an idea, but there was a point that you thought we would, a cutoff point where we may not have crossed, let's say. Can you tell us a little bit about that? What did you expect
how did those predictions pan out?
Yeah, exactly.
Well, we ran some predictions. They were actually pretty good. They said that the system could sustain deformation if one of our assumptions held true. It turns out that it not only held true, but it was even better than we anticipated. I had a number that I was keeping fairly close to my vest. I don't like to disclose things. I disclosed them as the test was going on. Martin and I were standing there watching it from overhang, looking at the test from above.
Well, according to our analysis, it should go all the way, except we have no idea how much rotation and axial pull the liner is going to take. Right. Eventually, it's got to go.
Eventually, it has to.
Okay, you've now surpassed IPEX.
Pretty exciting.
This is the largest displacement that we've imposed during our testing. You now are exceeding everybody.
We thought that maybe the lining system with the existing pipeline could tolerate on the order of about 2 feet, 0.6 meters of displacement, a fault movement. We typically run fault movements anywhere from 0.3 meters to 1.2 meters. We typically have a limit at 1.2. We could actually test to about 1.5 or so, but the way the box was configured, we'd have to move everything around. So we typically, if we can get it to go through 1.2 meters of fault strikes of fault displacement, then we can model the large scale movement behavior with respect to the pipeline.
I don't want, I'm sorry, Tom, to cut you off, but I don't want to get this to get too technical, but that cutoff line of 0.6 meters really depended on the adhesion level and the ability of the interface between the liner and the pipeline to propagate.
Yeah, it really depends upon how much you can transfer stretchability to the lining system without causing forces that cause a rupture of the lining system. So basically, the lining system for SANEXEN, and we used, I suspect you'll talk about this, Martin, but we used what's called an Aquapipe Generation 2 lining. That lining was able to detach itself from the pipeline, still maintain pressure and flow. One of the things we do in our tests is we run them at the water pressures that are actually operated when the systems are actually in performance. So we're one of the few labs that actually can do these tests and do the measurements with the precision and acuity that we're able to achieve, and do these measurements while the pipeline's under pressure. Mm-hmm. So we actually exceeded our 0.6 meter. We took the SANEXEN system out to the 1.2 meter limit. We couldn't push it any further than that. And
because of the limitation of the setup. That's
right. And we were able to determine that the lining itself, on average, had stretched about 6.3 to about 6.5%. It's a fairly large percentage. And hadn't shown signs of achieving failure force, where the forces that we measured were a maximum of about 30 kips, 30,000 pounds. And our estimation of the lining capacity was set at about 62,000 pounds. So we were well under the force requirements. And apparently we were under the deformation requirements. We had measurements that showed us exactly what the joints were doing, because the pipe pulls apart at the joints. As it pulls apart at the joints, the lining emerges. If you imagine a pipeline actually gets larger in its longitudinal direction, and as it stretches or gets larger, it can't stretch on the iron. It has to stretch at the joints. And the joints literally pull apart. and the lining emerges from the joints, and the lining has to take that stretchability, the force and the deformation capacity, and it has to rotate at the same time, because we actually do tests that cause the pipeline to extend and rotate. So it had to take both of these deformations, and it did it, and we measured it precisely. So not only do we measure it with our instruments that are getting measurements that pertain to the performance of the pipeline while it's being deformed, but after the test is over, we leave the deformation in the soil box and exhume or expose the pipeline. And then we have a special laser system, a Leica system, that actually runs lasers and measures the relative displacement of the pipeline. We take a measurement before we even bury it. And then we take a measurement afterwards, because we excavate it very slowly. And therefore we can determine after the fact what the final deformation was. That should obviously conform to what our measurements are telling us for the final deformation. The measurements do much more. They actually give us the full development of the deformation, but they should at least conform to what we're able to measure in the Leica system. And they did. They did quite well. They did very, very good compliance between all different measurement systems.
Have you seen that kind of performance in other products on the market?
I mean, we typically don't expect that a pipeline system will sustain the full 1.2 meters of movement. And they to perform well, they don't have to. But this particular product performed very well, and it did sustain that deformation. It could have sustained more.
You're referring with previous testing to brand new water mains and not lining materials, are you?
There are a number of systems that have been created to be able to move at the joints and therefore go through some of this deformation that I just talked about. And we tested some of those systems.
Before we go back to our original topic, Jason, a scoop for you, Tom. We last week received finally the testing on the coupons that were tested for the joint, from the joint, that were pulled out during the fault rupture test. And the results are clear. There's no significant difference from a statistical standpoint with respect to design specification of the product. So it looks like it's unaffected. I'm amazed.
Yeah, no,
it's really, like brand new.
What we did in these tests, again, SANEXEN is committed to high performance and quality. And we actually, when the test was over, cut up the pipeline and took out samples of the lining and samples of the pipe and sent it to SANEXEN. They wanted to perform their own tests to substantiate and back up some of ours. We also had our testing people go into those pipelines and measure the pipe wall thickness, the liner thickness at several different locations, so that we could conform and confirm the dimensions associated with the lining at several different locations along the pipe, and the dimensions of the pipe at several different locations along the pipe, and those have been confirmed. So not only was there follow-up testing, but there was follow-up measurements. And one of the measurements that's performed during the test is there is the lining that gets extruded at the ends of the box. And this is the same lining that's been put in the pipeline. And we take a portion of this extruded lining and it goes to SANEXEN for testing, it goes to Cornell for testing. And those tests confirm the behavior that from other tests that we have of the lining. And it's actually the results of those tests, which is the same lining that was tested, that we actually put inside our models to be able to interpret and understand the test results.
What drives you to develop these products? Are you responding to the needs of large cities, of more rural areas? What's creating this innovation at SANEXEN?
The pipelines are ubiquitous. They're all over the place. So you can't walk in a city more than, let's say, a half a dozen steps, and you cross a pipeline that's underneath you. Same thing within a building. And so we have this tremendous proliferation. There's a plethora of pipelines out there. So looking at the technologies associated with pipelines is a fundamental technology related to the way we live.
Late 90s, Montreal, the city of Montreal comes to SANEXEN. We have that huge problem with our leaking water main infrastructures. It's flooding our sewer system, and it cost us fortune to both get potable water distributed and then treat that water that's flooding the sewer system at downstream at the wastewater treatment plant. So we, being a technology developer, a technology provider with intimate know-how, knowledge of the environmental issues that we need to address, we developed this Aquapipe product. Now, nowadays, we're being asked by cities and water utilities. First question was from Toronto in their subway extension construction projects that they have. And they had a 12-inch water main, and they have a new tunnel that goes underneath. And they say, we can't dig. I mean, there's buildings, we're slightly outside downtown, but in a dense area. What can we do to prevent that pipe to subside? Well, put Aquapipe in. And so we did some testing, and that led to demonstrating that this was able to withstand all those outside constraints or conditions. Now, going to the United States, and especially on the West Coast, they heard about the resiliency of our product, but they want us to do more than showing good results on a small testing bench. And so we started a big program in the last 5 years to make our Aquapipe product even stronger and come up with the demonstration that they needed for them to use that product to introduce into their pipeline rebuilding programs. LA has a big one, San Francisco, East Bay Mud, and a number of cities along the West Coast, San Diego, Los Angeles, Las Vegas in particular. And that's how we got to develop that.
All large cities, basically, that are quite prone to earthquakes, if I understand correctly.
We obviously the larger utilities have larger budgets and larger liability as well to address, and their asset management program is generally far more developed. All those smaller cities have their own. A suburb city close to Montreal that's called Des-Ormeaux has had, I must say in the past, had huge issues with its water main network and the water main breaks. And they did pioneering work with us to use cured in place pipe and Aquapipe to address those issues. As a matter of fact, they've lined more than 50% of their network today. There's no cities on earth that has done anything close to that. Obviously, it's smaller. So in terms of absolute number, it's probably 60 kilometers. It's not 5,000 like in Los Angeles. But still, the statistics are very clear. They reduced their water main breaks by 88% doing so.
Oh, wow.
By rehabilitating, using most of it is Aquapipe, not all, but most of it is Aquapipe, like 90+%. And so we're pretty proud of them recognizing our technology and investing in rehabilitation techniques.
Were some of these larger cities that are in dire need of this type of technology, were they able to see the results of your tests, Professor?
So major cities like Seattle, like Portland, Oregon, like Vancouver, like San Francisco, like Los Angeles, like San Diego, etc. these are big cities that have earthquake performance issues, and the lining systems developed by SANEXEN can resolve and solve many of these. We also have other cities like New York that don't have such a big earthquake hazard, but as we learned, have a very big hurricane hazard, have a very big construction-related hazard. So these lining systems are hazard resilient insertions, right? So they not only provide resilience against earthquakes, but they provide resilience against hurricanes. They provide resilience against ground movements associated with urban construction, frost heave, et cetera, et cetera. So large cities don't have to be in an earthquake vulnerable zone. Many of them are to some degree, but other large cities may be less subject to earthquakes, but more subject to hurricanes and construction related features. These kinds of systems that we're looking at provide solutions to those problems also.
One of the key aspects of our collaboration with Cornell was that together we were able to build a consortium, let's call it this way, of stakeholders, us, a producer, our supply chain, of course, the experts at Cornell, and the users. Los Angeles Department of Water and Power, San Francisco Public Utility Commission, the East Bay MUD, the Municipal Utility District, were with us during the testing. They helped us design the testing to some extent. They provided samples for the testing as well. And they all witnessed what we did. And I must mention as well that the city of Dollard des Ormeaux was as well with us, and probably the most knowledgeable of the people from the utilities from a lining standpoint. And Madame Anna Polito was there, told us, well, I knew it. We've done that all the time. I mean, this was no surprise to her, but the people at LA, San Francisco, and Oakland were thrilled, but not nearly as much as I was and my colleagues were during the testing. I was like a feather, confident, but I mean, in the expectative of, how far will we go? And I don't want to brag, Tom, but beating your setup was really good.
Well, we do something which is a little unusual, and that is when we do the large-scale fault rupture test, we invite the sponsor and whoever the sponsor wants to invite to come along and watch the performance. And a lot of labs won't do that because they're concerned about it not working. And our attitude is, well, our responsibility is to get the test set up so that it is accurate and as realistic as we possibly can. And there's no flaws introduced because of wiring difficulties, because of construction difficulties, because of instrumentation problems. And that's quite considerable, but our feeling is that's our responsibility, and it's the responsibility of the product to take it from there. So we try to do real tests, and we invite the real people who are responsible behind these tests to attend them. And that's a big risk, but it's one I think that's worked very well for us because the performance is what it is. We can validate that what we've done is conforming with reality. And the performance then is something that we capture in the experiment, but it is seen and observed by all the people that we invite to attend.
Exactly. That's the ultimate third party testing. So yeah. It's independent, it's third party, obviously, but it's real time. As you get the results, they're being communicated, and you can't get tougher than that to test. I mean,
it keeps me up at night sometimes.
Yeah, for sure.
Are challenging.
There are no stones that were left unturned to make that test a success, for sure. That's our job.
I watched a fantastic short documentary that was made about your time together doing these tests, and you seem reluctant, Professor, at some point to actually say how SANEXEN has outperformed everybody else that you've seen before. Now, is that truly the case, or did I misunderstand what was said in the documentary?
The performance is a matter of record, right? So again, because we have a lot of first and third parties watching, that's part of their observations. The testing data are also part of the observations. We don't change the data. We may interpret it in ways that are associated with our analytical capabilities and understanding of the pipelines, but we always put out what the instruments say. Other people can interpret as they would. We have our own interpretations, which we can back up, and we put forward in a report for the client. So yeah, it's a matter of record in terms of the test. I don't like personally to get into direct comparisons because one has to make a decision in terms of what's best for a system. So our commentary, or my commentary, is one that's principally associated with the SANEXEN product. And I can certainly say that the SANEXEN lined pipeline went through the entire range of deformation that we imposed on it, and actually performed extremely well because we were able to capture all of this joint movement, all of the debonding that occurred along the pipeline, the different loads, the different deformations, and so forth. So we did a thorough and complete job. The other thing that was pretty impressive was, we had the pipeline strain gauged at 20 different locations, and we subjected it to a whole heck of a lot of ground movement. Now, the instrumentation has to conform to this deformation at the same time as the pipe is. And if it doesn't, then we lose the instruments. We don't have any further measurements. Well, I'm happy to say that 19 out of those 20 produced results that we actually can know definitively where the debonding, the detachment that occurs between the lining and the pipe, exactly when it occurred during the test at each of these 19 different locations. So the instrumentation also did extremely well. I'm very proud of the research team that put this together because, of course, I don't wire the pipe. I might supervise where the different stations are located, but I don't do that specific task. That's down to the personnel who run the tests. So that's very important. Jim Straight is our laboratory manager, and he had a tremendous influence on the test results, as well as a number of people. We had Blake Berger, who came back. We had Brad Wham, who came back. They used to be research managers in our laboratory, and they actually came back to participate in some of these tests. We had a wonderful crew of student researchers. They all did a great job, and that's reflected in the extremely impressive performance of the instrumentation throughout the test.
How could a major city really use the benefits of this new Aquapipe technology?
We've summarized all the benefits of this technology into a value proposition. And if we take Los Angeles, the Los Angeles Department of Water and Power, they have in the vicinity of 6,800 miles of water mains in their network. That's water mains that we can address. And they need to change 1% of those 6,800 miles per year to have a turnover rate of 100 years. And doing so, they need to change, therefore, 68 miles of water mains. So in reference to 68 miles per year of pipe renewal, you get savings of 37 million cubic yard of water that won't leak anymore out of the network. You get 23 kiloton per year of greenhouse gases That's huge. That's the impact of around 20,000 vehicle per year.
I'm sorry, how are you saving on gas when you're changing pipes? Let me understand that.
Well, instead of opening the whole street, you're opening up only a few pits. The time you're on the scene is reduced by 3 times at least. You're not building new pipes. You're not using ore to build the pipes, whether they're or plastic or petrol or methane to do the plastic. You don't change the asphalt. You don't fill up the street back. You don't drive that soil out somewhere else. So the environmental impact of doing a cured in place renewal instead of opening up the street and changing everything is huge. And that's how you change on fuel, you save on fuel, on greenhouse gases and so on. And talking about fuel, again, those 68 miles would equal to 2.1 million gallons of fuel saved in 1 year. And that's additive. Year after year, you'll save that. It adds up to 1.1 million tons of soil. So I know it's a lot of numbers, but 1.1 million tons of soil is 69,000 trucks that are not in the streets. And obviously, when you use Aquapipe, you use it downtown. Heavily dense area, a populated area, when you don't have the luxury of opening up the street, you see what I mean? So that's 69,000 trucks that are not into our downtown area. That again, with those 68 miles that we would do in LA, that's huge impact. It's very tangible, social, environmental, and economic impact using our technology. And again, referring to LADWP, we would contribute to reduce the number of breaks per 100 miles that they have. Currently, they have around 17 breaks per 100 miles. And looking at the numbers we've had with the thousands of miles that we've lined so far, every line that we would install would be resilient for years and years. We warranty for 50 years. We're working on a demonstration that it would be for 100. So every section would not break anymore. So that statistic of 17 breaks per 100 miles would reduce significantly. If I use the example we saw during the talk today, that suburban city of Montreal reduced by 88% their number of breaks per year, per miles, by using our technology. So the impact would be very, very real. And just to finish, we do that, adding that seismic resiliency to whatever we line. We do that at a rate of, let's say, 500 to 1,000 feet per half a day per crew. So we could do, let's say, 1,500 to 2,000 feet per day per crew of that goodness, if you like, of that good work. And other technologies, open cut technologies that are seismic resilient, you can install less than 200 feet a day per crew. So we're doing 10 times more than they're doing. And with all those environmental benefits, with all those social benefits, and of course, with all that taxpayers' money saved. So there's a lot of benefit in using our technology, long-term, short-term.
I'm starting to understand why you call it a game changer.
It's definitely a game changer. Those results at Cornell, and thanks, Tom, were amazingly good, above our hopes. We knew it would be doing well. But that well is amazing. Here's how it works when a pipe lined with Aquapipe is subjected to a larger formation. It stretches the pipe because the pipe is moving in the ground. There's stress transferred to the liner. And if the liner is able to withstand the strain that stress imposes, and at one point debond from the pipe so that that stretching can propagate to long distance, then you have a resilient behavior. And that's exactly what we have. And our product is able to withstand 20% plus of such stretchability before breaking. Now, brand new seismic resilient products have joints that have the ability to move. But that movement is restricted and is fairly limited in size. Not more than 6 inch over 20 feet, 5% at best, probably less. So there's a limit and it won't go beyond. And we could go 6, 7 during the fault rupture test. We could go 10, 12. I wouldn't go more than that. But we have on paper up to 20+% of the formation capacity before any real damage is produced to the liner. And that's how it's so different from all other results that are publicly available on Cornell's website, Tom's laboratory's website at Cornell.
The SANEXEN lining, the AP2, has not failed. So it gets both extended axially and it gets bent out of plane. So the joints where the lining becomes exposed to the soil actually rotated and extended. It's as good a test result as one could imagine.
So this is the only solution to replacement. So instead of opening up streets and affecting traffic for months, we access the pipe from the ends and then we repair and renew the pipeline from the interior without affecting the street.
Le produit pourrait être très bien adapté pour des endroits où il pourrait avoir des mouvements sismiques.
Important landslides, flooding events, hurricanes, high tides. This is a solution for it because it makes the pipe simply reliable.
How much of this have you implemented already?
Into a product?
Yes.
We see our product as a solution for safe and clean water for generations, no matter what. You put it in the ground and that's the last piece of repair or renewal for that section you'll ever do. That's our vision. That's what we want to do. And we've achieved it. When it's only the water main you need to fix and make reliable again, well, there is a solution.
Yeah, it's just thinking of COVID here in this situation, I realize how important the lack of disruption to the community is. It's really remarkable work. I didn't realize it based on my research before speaking to the both of you, but clearly the advantages are vast. And clearly this is the right choice for any city, for any community, especially the larger ones, obviously.
We certainly believe so. And now the real job starts. We need to install that into cities and bring that great solution to all our customers.
Yeah, there was a comment that I made earlier about the fact that this was not just a fault rupture test, it was a series of tests that led up to a fault rupture test. And we have a particular protocol that we follow, and I commented a bit about the different types of tests. We do tensile coupon tests, we do direct compression, direct tension, 4-point bending. Sometimes we'll do axial load conveyance from the soil to the pipe. We did those with SANEXEN, but we did more. We actually did special, what we call friction tests, so that we could improve our numerical simulations. We actually had a section of pipe that was dragged across a lining that had been created by SANEXEN, and we could actually measure, as the pipe was being dragged across the lining, the development of force axially in the lining. as a function of displacement, as a function of the internal pressure that we applied. So we applied from zero pressure to 80, 85 pounds per square inch. So we were able to do some very special testing that way. We did special direct shear tests where we actually took the lining that had been adhered to a particular pipe and actually moved that lining with respect to the pipe, which would happen during an actual performance, and determine the friction coefficient that existed between the lining and the interior surface of the host pipe. Before we put the pipeline in the box, had done special laser scans so that we knew the variations of the diameter and could piece together the different pieces of pipe and know exactly what the interior dimensions were as precisely as possible so that we could understand that contribution to the pipeline behavior geometrically. So not only did we follow the normal protocol, which is quite rigorous and quite specialized, we actually had additional components to that protocol that we applied to the SANEXEN.
Martin speaks of not having to touch these again for generations. It seems like you've done the testing accordingly to ensure that he knows what he's talking about.
Definitely. We're very glad to have worked and continue working with you and your team, Tom.
The same with us, Martin. It's been a pleasure.
I'd like to acknowledge the support of the Canadian government, the Sustainable Development Technology Canada, for the support in funding and also designing of this testing program, as well as Tom's team, of course, for building the program with us, and our sponsors, LADWP, SFPUC, ISBMAD, and DDO.
And thank you, Mr. Martin ORourke.
Thank you, Jason. It was a pleasure.
So that was Professor Thomas Denis O'Rourke of Cornell University and Martin ORourke of SANEXEN. I'm Jason Rohde from NOMAD Creative Studio. Stay well.